So today we're going to be looking at the integral of e to the negative x squared, going from negative infinity to positive infinity. The name of this integral is the Gaussian integral. Now, normally it is told to you that there is no elementary solution, which is true. And so what we're actually going to do in order to evaluate this integral is we're going to go into two-dimensional space dealing with Cartesian coordinates, and then we will be converting that into polar coordinates in order to work an answer out for the value of this integral. But in order to do that, first thing I need to do is show you what a Jacobian is and what the purpose of the Jacobian is. So we start out with our rectilinear space, and we find some random point P in that space. And from that point, we know that the distance to it, which we'll call r, is basically the square root of the x squared plus the y squared values. So we know that the two legs are x and y. And to go a step farther, not only do we know that, we also know that the line r makes an angle theta with the x-axis. So now, from there, we can construct a transformation space, which basically is that our x and y terms can be written in terms of r and theta. So now we have all the information we need. We can start to construct the Jacobian. And here's the definition of the Jacobian. It's just the determinant of all the different partial derivatives that are possible that are first order. So then, solving these guys out, let's just walk through it real quick. The first one is the derivative of x with respect to r, which is just simply going to be cosine theta. The second one is x with respect to theta. The derivative of cosine we know is negative sine theta, so then we know that that is going to be negative r cosine theta. Sorry, negative r sine theta. Now we look at y with respect to r, which is just sine theta, and then we look at y with respect to theta, which is going to be r cosine theta. And we know from here that now we're just solving for a determinant. So we have r cosine theta times cosine theta, which is going to be r cosine squared theta. And because of this negative right here, we know that when we're subtracting in the determinant, that now becomes addition. And so we have r sine squared theta. Just pull the r out of these terms, and you have cosine squared plus sine squared, which we know by definition is equal to 1, because that is the unit circle. So then we get that the Jacobian of this space is simply r. So now we have the information we need in order to do coordinate transformations from rectilinear coordinates to polar coordinates. I'll leave that up for a second before erasing it, so you can pause it, study everything a little more closely, and see where it all comes from. So now back to the original integral that we cared about. Now there's a great thing with this going on right now, and that is the variable x itself. It doesn't always have to be x. In the specific configuration that everything's in right now, we can call x a dummy variable. So it can actually be turned into anything we want. So let's call it y now. So now we know that both of these integrals are going to have the same value, because there's nothing really special about x and y other than the fact that they are different variables. So now, multiplying these two together, and from here, we can actually use a property of reversing separation of variables, because we know that the x and the y do not depend on each other, so we can actually take one inside of the integral of the other. And then adding exponents together, we now have this integral. So now the next thing we want to do is we want to do our coordinate transformation. So that means that we want dy dx to be something that's dr d theta, but don't forget we need that Jacobian in the front. And also we have x squared plus y squared right here, which we know is r. But we know it's r squared. So the only thing to mention here is that this guy is simply that in order to do a coordinate transformation like this, you just need to remember in front of the new coordinates, you need to multiply by the Jacobian. And so because of that, we can actually rewrite this and just to kind of go over everything here, the 0 to infinity is because now we are dealing with polar coordinates. So you're just going from the origin out to some distance. It is perfectly valid to think of that in the same way that you would have thought about x going from negative infinity off to infinity. It's just that now, because we're in polar coordinates, everything is with respect to the origin. And then the 0 to 2 pi is we are going to traverse an entire circle. And then, again, just the Jacobian times the coordinate transformation. So now we're going to move this guy up to the top, and we're going to solve it out. So the first thing we're going to do is we're actually going to work on the d theta term first. And so from there, all we're going to get from that is 2 pi. I do notice that my integration, the order of which may be a little off to you, but just remember that as long as you keep track of which terms are capable of going in between which values, you should be able to still keep a good handle on which integration term is at which point. And you would also just do a separation of variables at that point, because how we have it written, r does not depend on theta at all. So you can actually just pull the 0 to 2 pi d theta out from the whole thing and just multiply through, and that'll get you to the 2 pi that's right here. Now this term, we like this term a lot more than our original term, because now we can use u substitution. And so now we see that RDR is just going to be minus 1 over 2 du. And yet again, okay, so there is a minor mistake here. For the coordinate transformation, you just want to use r squared. You don't want to use minus r squared. And you're going to see why here in just a second, why that was a bad idea. But everything else still works out exactly the same as it had. It's just replace all your minuses with pluses, and we're good to go. So now the next point is just integrating e to the minus u. And we know that the integral of e to the minus u is just minus e to the minus u. And we see that our 1/2 and our 2 cancel each other out. All right, so what happened here is I'm taking advantage of that minus sign, because we know that a negative integral, you can actually take your bounds and just flip them around. So instead of being from a to b, it is now from b to a. And that's what I did here, and you'll see why that's so beneficial here in a second. So now we see what the benefit of doing that was. So we don't have to worry about keeping track of minus signs. The negative is on the 0, so we can just completely ignore it. And so now we have I squared equals pi. And so all we do now is just take the square root of both sides. this is the value of our desired integral. Because we do know that for the Gaussian function, or the error function, however you wish to say it, but the error function is actually this term with a constant in the front. But we know that with the Gaussian integral, that the area under this curve is the square root of pi. Take it from 0 to infinity in the x domain, and it's the square root of pi over 2. Anyway, that is how you do the integration for figuring out e to the minus x squared, figuring out what the value of it is over all terms within its domain. I hope you enjoyed this video. I do apologize for some of the mistakes I made. But other than that, hope you have a good day.